Hello everybody, welcome back. Today we're going to be taking a look at a three variable optimization problem with a constraint. Okay, so a box has three of its faces in the coordinate planes and one vertex on the plane with this equation here. So we're supposed to find the maximum volume for the box. So here's our box here. This face is in this coordinate plane, that face is in that coordinate plane, and the same with the back one there. Um, and then it has one vertex that is off of all of those, which is this one, x, y, z. And you can see that the volume of this box is going to be x times y times z. So with that and this here, we could solve this for one of the variables and substitute that into here, and then do our typical optimization thing from there. But that is going to require a lot of effort and algebra. So we're going to be taking a look at a slightly different way to do it that looks kind of weird. It's kind of tricky, um, kind of sneaky in a way. Um, so we're going to say here that we're going to have a different function here. That's a function of x, y, and z. And it's going to be our volume function plus a constant. Okay, so this is going to have a maximum value at the same point as our volume function would. It's going to be a different maximum value, but the point at which the maximum value is going to be is not going to change. Yeah, so this c here is arbitrary, but we're going to set it instead. We're going to think of it as 6 lambda. And if that is the case, we have this equation here that tells us that 6 is the equation of our plane. 6 is equal to that. So our f function becomes xyz plus lambda times our plane, which is equivalent to the constant 6. So now we have turned our three variable optimization problem into another three variable optimization problem. It's different though because we have our constraint included now, whereas before we couldn't optimize this by itself. Our constraint was separate. Now we have it all combined together in the same thing. So we're going to take the different partial derivatives of our f function, which remember, since this is a constant, and we're adding it, that it's going to be the maximum value of f is going to occur at the same xyz point as for our original function. So we're going to take del f del x, which we can see is going to be yz plus 2 lambda. And for del f del y, it's going to be xz plus 3 lambda. And then we're going to have xy plus 4 lambda. And we're going to multiply these all by their respective coordinate. Well, okay, before we do that, because we can do that because we are setting these all equal to 0 to find where the maximum point is. So, since one side is 0, we can multiply the other side by whatever we want as long as we do it correctly. So this ends up x, y, z plus 2x lambda equals 0. This is x, y, z plus 3y alpha, or lambda is equal to 0. This is x, y, z plus 4z lambda equals 0. What we're going to do here is we are going to sum these all. So this gives us 3xyz plus, we're going to distribute out the lambda, 2x plus 3y plus 4z, and this all equals 0 still. So yeah, does this look familiar at all? We are just, after all, adding a constant. So this is equivalent to saying this, since we can substitute back in the equation for our plane. And we can rearrange this to show, so we take that over there, and then we divide by 6. So we have lambda equals xyz over 2. Okay, so now that we have this, we can substitute this value back into our equations here. And we will get some more relations that we will be able to use to find the answer. So, substituting this, bringing that over to the other side of the equation, we get yz equals xyz. Then we get, for this one, we get xz equals 3 halves xyz. Then we get xy equals 2 xyz. We can see that a lot of, the yz is going to cancel, the xz is going to cancel, and the xy is going to cancel. But when you cancel these out like this, you got to remember that there's always an understood 1 on the other side of the equation because you're dividing it over. So our x is equal to 1, our y is equal to 2/3, and our z is equal to 1/2. And then the actual question asks us to find the maximum volume, so we substitute that back into our equation up there. V is equal to 1 times 2/3 times 1/2 equals 1/3. And that is our answer. Now if you were a little confused about how this works geometrically, I can show you a little better drawing than the one here. Okay. So here we have our plane, and we have our box and everything here too. For some reason it is not allowing me to, out there. I was clicking all over the place and it wasn't doing anything. So here's our plane and here's our box. We can move this point anywhere on this plane and it'll give us our box. And so there's the coordinate face, there's a coordinate plane, and that's the other one on the back. And it also calculates our volume for us, which we can see here. So, obviously the closer you get to each of the coordinate axes, the smaller the overall volume gets. But then this point here is the one that actually gives us the maximum volume. We can see that as we get close to it, our volume does approach that 1/3 that we calculated, and barring that we don't take it into the negatives, that is, we never get a value for that is larger than 1/3. So thank you so much for watching, and I'll see you again in the next video.